I'm Alex Turner, and today I'm going to talk about some work from the Beacon project at UC Berkeley led by Professor Ron Cohen's group. Specifically, I'll be talking about our work using a dense, low-cost sensor network to observe CO2 emission changes from the transportation sector with a focus on changes induced from the COVID-19 global pandemic. This work I'll talk about today is going to focus on the San Francisco Bay Area, and this background image is the Bay Bridge in San Francisco. I find it striking because it's totally empty, like many of the roads were during the peak of the shelter-in-place orders. There's been much speculation and discussion about the impact of mobility restrictions due to COVID-19 on carbon emissions, such as this article in the New York Times from Brad Plumer. Yet it's been difficult to actually quantify those impacts. So an obvious question is, what are the effects of shelter-in-place orders due to COVID-19 on urban CO2 emissions? San Francisco was the first U.S. city to implement a shelter-in-place order, which I've shown here on the left. The order was enacted on March 16, 2020, or 214 days ago. Because it was the first city to enact such an order, we might expect the most abrupt response here. Now, before I go into the specifics of the changes observed during COVID-19, I wanted to talk about how we actually go about estimating emissions. There are two methods that I'll discuss, the bottom-up method and the top-down method. On the left, I'm showing a little cartoon of how the bottom-up method works. It can sort of be thought of as an accounting method. We take some activity data, such as the map of traffic density and emission factors, like the CO2 emitted per car, and the product of these two gives us a map of CO2 emissions from traffic. This method is great because it relates the CO2 emissions to the underlying processes driving those emissions. However, it requires a lot of detailed information at high spatial resolution and requires assumptions about how representative those emission factors are. In contrast, the top-down method attempts to back out the most likely set of emissions given a set of atmospheric observations. This cartoon on the right shows a simplified schematic of how this works. Briefly, we use a transport model to simulate what our measurements should see, and then scale the emissions so they best fit the observations. This top-down method is often used in conjunction with the bottom-up method, or that is to say, we use the bottom-up estimate as the starting point and then trying to find where the bottom-up is over or underestimating emissions. Our group has spent quite a bit of time putting together what we think is the best bottom-up estimate of urban CO2 emissions in the San Francisco Bay Area. In a moment, this animation on the left will show what our emissions look like. The row on top shows a spatial map of the emissions over the whole region. The left panel is the entire domain, and the right panel is zoomed in on the San Francisco Bay Area. Then the bottom row shows the emissions from different sectors over a week, with black as total, orange is traffic, purple are stationary anthropogenic sources, green is the biosphere, and the background shading indicates daytime and nighttime. There are a couple features I'd like to point out. I'll start with the biosphere, or the green line on the bottom. So our biosphere estimate comes from measurements of solar-induced chlorophyll fluorescence from the Tropomi satellite. We see large uptake of carbon from plants during the middle of the day. Moving on to traffic, we also see a daily cycle in the traffic emissions in orange. This comes from a high-resolution traffic inventory that was put together by Brian McDonald, who's now at NOAA. The emissions from traffic can be clearly seen in the top right panel as well. And then putting it all together in black, we see a sawtooth-like pattern in the daily cycle of CO2 emissions over the Bay Area, with the biosphere offsetting much of the midday emissions from traffic. Our aim here is to improve on this bottom-up estimate shown on the left using our atmospheric measurements from the Beacon network, which I'll talk about in a moment. The Beacon network was established in 2013, and the aim of this project was to really blanket a city with sensors. And this was in contrast to most studies at the time that were using about 1 to 5 sites to sort of characterize urban CO2 emissions. There's actually now more than 60 sites in the Bay Area, and what I'm showing on the left are just the 35 sites that were active during the beginning of the COVID-19 shelter-in-place order. So what we're actually measuring each of these sites is CO2 using a Vaisala. We're also measuring CO, NO, NO2, and ozone using AlphaSense, and PM using a Shinye. And the studies at the bottom give more details on some of these measurements. So how do we actually use these measurements to infer emissions? Well, I'll give sort of a cartoony example here. So let's say we're measuring CO2 at this site here in Oakland, denoted by the X. So maybe for the first week, we see air that's coming through the Golden Gate Bridge to our site. And during that week, we generally measure low but variable CO2 concentrations. Then the following week, let's say that the air masses now travel this path here, which sort of follows the highways, maybe not a very realistic pathway, but in any case. During the second week, we might instead measure CO2 concentrations that are notably higher, but still somewhat variable. So what this would imply is that there's some source along this red trajectory that is not present on the yellow trajectory, and it would imply there's a source in the urban area. And so we could use that to back out the emissions. We can say this more explicitly, or more quantitatively, by saying that our measurements are y, or a vector, and our emissions are x, and there's some model h that maps between the emissions and the measurements. So if we were to solve for y, this is known as a forward problem. It's a well-posed problem with a unique solution. In contrast, solving for x is an inverse problem, and it's ill-posed and may not have a unique solution. That's to say, there are many locations along that red pathway I showed that could have emissions and lead to identical measurements at our site downwind. So what we want to do is find the most likely set of emissions that give us those observations. So what we're going to do is use Bayesian inference to find the most likely emissions given our measurements. All right, what I'm showing here are all the beacon measurements from January to July 2020. The top panel shows the concentrations with each color denoting a different site, and the bottom panel shows the number of sites active during this time period. We did a fair amount of site maintenance in January and February and got a lot of sites online right around middle of February, which ended up being fortuitous for the impending shutdown. So for this work that I'm going to show, I'm going to indicate two time periods. This gray bar is roughly when the shelter-in-place order was enacted, which was mid-March. We're going to leave this week out of the following analysis, and we're going to define a period before the shelter-in-place order due to COVID-19 and a time period after that order was implemented. All right, so what I'm showing here is the data before shelter-in-place in purple and during shelter-in-place in green. The before shelter-in-place time period is defined as February 2nd to March 14th, and during shelter-in-place is March 22nd to May 2nd. The solid line is the median across all the measurements, and the shaded region is the interquartile spread. So there's a couple things that we can clearly see. First, we see the biggest differences between the before and during periods occurring in the middle of the week, primarily early on in the day. For example, on Wednesday, right around morning rush hour, we see almost a 50 ppm decline in CO2 concentrations between these time periods. We see this on Monday. We also see it partially on Tuesday, Wednesday, and Thursday, and weaker on Friday. The weekend concentrations don't really show much of a difference. We also see similar signals, for example, on Wednesday in the afternoon or the evening rush. So what we're seeing here is a clear decrease in CO2 concentrations. But that still begs the question, how much of this is actually attributable to emissions? And really, we need to account for meteorology and atmospheric transport, because there could be differences that are driving some of those differences in the observed CO2 concentrations. So going back to the expression from earlier, y is our vector of observations, and x are the emissions. And there's this matrix H that represents the atmospheric transport, or the meteorology. Really, it's the way of mapping between the emissions and the observations. So here, we construct this H matrix using, it's called STILT, or the Stochastic Time-Inverted Lagrangian Transport Model. And what it does is for every measurement you make, we advect hypothetical particles 72 hours backwards in time and look where they came from. And we do that using no high-resolution rapid refresh meteorology. And so doing this, we can then figure out where those air masses that got to our sites came from. And what I'm showing here on the left is the cumulative influence of our network, or really the region that our network is sensitive to. Now if I zoom in, you can see that we have the strongest sensitivity over the San Francisco Bay Area. So this means that emission changes that occur here, we would be sensitive to. And this white line indicates the 40th percentile of this cumulative influence. So we define this as the region that our network is sensitive to, or where we can constrain emissions. Now we can bring this all together and start actually estimating CO2 fluxes during the COVID-19 global pandemic. All right, what I'm showing here are the CO2 fluxes observed before shelter-in-place on the left and during shelter-in-place in the middle. The hatched area indicates low sensitivity from our network, as I mentioned before, and a few things that we see pretty clearly. One is that there's fairly negligible differences outside the hatch domain, aside from the biosphere, which is constrained by satellite measurements. The one notable biosphere signal we do see within our domain is here on the north end of Richmond. And I've zoomed in with an image from Landsat. And you can also see a purple point source nearby, which is the Chevron refinery. So we see a pretty large decrease over this domain, primarily in the urban cores and along crucial freeways such as the I-80 freeway. So this implies large decreases to traffic CO2 emissions during this time period. Alright, what I'm showing here is the Bay Area CO2 fluxes before shelter in place. What we're finding is large CO2 emissions from traffic in orange that coincide with the morning rush hour during the middle of the week. This is not simply driven by the prior emissions, and it's notably absent during the weekend. Now I've added the bottom panel here that shows the same thing, but for the time period during shelter in place, and we see pretty dramatic differences. We're seeing a 30% decrease in the emissions from fossil fuels, with most of this coming from traffic and a small change from stationary anthropogenic sources. Two particularly interesting findings are the changes to the diurnal patterns. We no longer see those large rush hour emissions, and the nighttime emissions show a dramatic decrease during shelter in place. This is pointing to a major shift in both when and where our CO2 emissions are coming from. Finally, we also see a much more active biosphere during shelter in place, and this is because this occurred during spring 2020, which highlights the importance of using measurements to help constrain that signal. In summary, we're finding a 30% decrease in urban CO2 emissions in response to COVID-19 mobility restrictions that's primarily driven by traffic. These findings were only possible because of the dense sensor network employed here, and it really highlights the power of being able to get these high-resolution spatial patterns. I've also included some additional details about the inversion here. With that, I thank you for your time.